We're going to talk about the law of logs, log rules. If you have log base A of B equals C, it must be true that A is bigger than 0, B is bigger than 0, and C is any real number. And the reason is this equation means A to the C equals B. Now, suppose C is the square root of 2 and A is -4. Okay, I understand what 4 to the square root of 2 is. Can even calculate that on my calculator. The problem is, what is a negative to the square root of 2? Now, I know if you have -3 to the 5th, in terms of the sign, it's a negative times a negative 5 times, which is a negative. And if it were 15 times, it would be a negative. And if it was 6 times, negative, 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 4, 5, 6 times, it'll be a positive. But what is a negative to the square root of 2? What is a negative to the square root of 2? Like for example, I know that 1 to any power is 1, so the 1 isn't the problem. I know that 1 to the... So if somebody asks me, how much is -3 squared? I can do this, and I advise everyone to do this in 2 steps. A negative squared is positive. You don't have to write the positive. And the 3 squared is 9. When students get really confused sometimes, they have to do this, because they try to do the whole multiplication at once. But once I slow them down, what's a negative times a negative? Positive. 3 times 4 is 12. So I know that this down here is gonna be 1. But what sign goes there? How much is a negative times a negative times a negative to the square root of 2? Makes no sense. That is why this A must be positive. Now, why is B positive? In theory, B does not have to be positive. It just works out that way. See, A has to be positive because otherwise it may not make sense. Now, this statement means A to the C is B. And if A is positive, A to any positive number is positive. A to any positive number is positive. Equals a positive number. But A to the power, A to any power, sorry, blew that one. A to any power is equal to a positive number. But A to the power is what is going wrong here? I got it. I wrote this down wrong. A to the C. Okay. A to the C, which is a positive number, is equal to B. Okay. A to the C is B. So if A is positive and you raise it to any power, you'll get a positive answer. If you don't believe that, if you raise 2 to the 0, you get a 2. If you raise 2 to the 1, you get raise 2 to the 0, you get 1. 2 to the 0 is 2. 2 cubed is 8. You may say, well, what if the power is negative? Well, this becomes 1 over 2 cubed, which is positive. 2 to any power is positive. 12 to any power is positive. I know this is 1, this is 12. Let's make this 2. I know 12 squared is 144. So if you have 12 to a negative power, you have 12 to the negative 2. This is 1 over 12 squared, which again is positive. The graph of a to the x for any positive x always looks like this. It's never 0 and it's never negative. So a to any power is positive, but a to the power is equal to b. So if b equals a to the power, and a to the power is always positive, then b is always positive. And the number c, as I denoted, it can be any real number. It can be 7, it can be 1/3, it can be the square root of pi, anything. Now we have some rules. And one rule is, if you have log base a of a product, this is the same as log base a of x plus log base a of y. Now we do have a couple constraints. Remember, b has to be positive. So this has to be positive, that has to be positive, and that has to be positive. Just remember that -3 times -5 is positive, but it does not equal to the log of -3 plus the log of -5, because those numbers are not negative. Sorry, those numbers are negative, but you know, -3 times -5 is the same as 3 times 5. And now it's okay. Okay, so it depends how you break up x, y. So that's one rule. Log of a product is the sum of the logs. Just sum them up. But just make sure that that's positive. That is log base a of -15. It does not equal to log of 5 times plus the log of -3, because this is -3 times 5. And the reason is, this makes no sense. You can't take log of a negative number. This here makes no sense. But even if some magic happened where they were both +3, if the right side makes sense and the left side is nonsense, they're not equal anyways. Let us prove this. So let's write it down nice and neatly. Log base a of xy is equal to log base a of x plus log base a of y. So I want to prove that the right hand side equals the left hand side. I'm going to call that u, and I'm going to call that v. So what we have is, from here, that a to the u is x, and from the second one we have a to the v is y. Now if I multiply x and y, and my motivation for doing that is, on the right hand side it's multiplied. So it's x times y, which is any way of writing x, which is a to the u, times any way of writing y. So xy, using the same bases, we add the exponents. But this statement is the same as u plus v is equal to log base a of xy, because a to the u plus v should equal xy, and that's what it said. But what was u? U was log base a and v is log base y. So u is log base x plus v is log a of y, and this equals to the right hand side. So yes, this does equal to that. It really is true. Okay, I want to write this neatly again. So the first rule that we have is that log of xy is equal to log of x plus log of y for any base, but they all have to be the same. Now the second rule says that log base a of a fraction, this is equal to log base a of x minus log a of y. Division becomes subtraction. Let us prove this. So I want to get the left to right hand side, this right here, to equal this. Okay. So if I call this u and that v, that would imply that a to the u is x, because log base a of x I'm calling u. So a to the u is x. And likewise, if I'm calling log base a of y v, then a to the v is y. A to the v is y. And I'm motivated to divide the two. X over y, well, x is the same as a to the u, and y is the same as a to the v, and this simplifies to a to the u minus v. So this is equal to that. But that's the same as log base a of x over y equaling u minus v, because a to that power, which is right here, should equal to x over y. But that's what I said. Okay, so just recopying this in a little bit of a different language, no u's and v's. U was log base x, log base a of x, minus v, which is log base a of y. And I proved it. It's not because I told you that statement is true. I proved that it's true. Don't accept anything that somebody tells you is true, even if you're sure they're right. I'm not suggesting they're wrong. I'm just suggesting that you should prove it on your own. Now, the third statement says log base a of x to the r. You can bring down the power in front. It's r times this. Now, just like 1 and 2 can give you trouble. For example, log base a of negative 2 over negative 3. That's okay, because that equals to log of 2/3. But you can't say that it's log base a of negative 2 minus log base a of negative 3. This side is valid. It makes sense. But this doesn't. You can't take log of a negative number. You can't take log of a negative number. You can't subtract two things that don't exist. So it doesn't equal this. But if you ignore this moment and you did plus 2 and plus 3, yes, those two are equal. These two expressions are most definitely equal to one another. Alright, so now how do we prove number 3? Well, how about I let u equal log base a of x to the r. So a to the u is equal to x to the r. Now, I want it to equal this, but this only has a as the base, not a to the u. So I think, what can I do to a to the u to just get a? And the answer is I raise it to the 1 over u power. Because when you multiply those powers, you get 1. And a to the 1 is a. So this is equal to x to the r over u when I multiply those powers. Okay. So now if I write log base a, did I do the division the wrong way? Yeah, I think so. I prefer just to get a to a power equals a constant. So what I'm going to do over here is I'm going to raise both sides to the 1 over r power. So on the left side I get a to the u over r, and the right side I just get x. So writing this logarithmically, we get log base a of x is equal to u over r. A to the u over r equals x. Exactly what it says there. Okay, we're getting there. Log base a of x is u. Just remember, I let u equal log base a of x to the r over that r. So now if I multiply both sides by r, this r cancels out, and the right hand side is log base a x to the r, and the left side is the left side. But that's what I wanted to prove. Wanted to prove that that power can come in front, and it has been established. Now there's still what's called domain problems. Like if you have -2 squared, that's okay because that's log of 4. But so this is okay. If you bring the power down, that's where you have trouble because you're taking log of a negative number. However, I'm not saying this is always wrong. If you have log of 2 cubed, it most certainly does equal to log base a of 2. That is true. Just when you bring down the power, what's left over can't be negative. This is not negative. There it is. And when I brought the power down, it's not negative. Or 0. So I can take the log of 2 for any base and then multiply that by 3. That is 100% allowed. Now, there's one more rule that I think you should know. If you have log base a of b, this is equal to log of base any choice you like. Of course, the base has to be positive. Log base c of b divided by log base c of a. For example, if you needed to find out what log base 2 of 3 is, well, it equals some number. 2 to what power gives me 3? I don't know. I have no idea. And my calculator doesn't have a base 2, a log base 2, but it does have log, so I can take log base 10, so c is 10, log base 10, and the b goes on top, which is 3, and the base goes on the bottom, which is 2. Now I can use my calculator to figure this out. But as I said, you can use any base that you like. Well, I choose to use base e. So it's log base e of b, which is 3, divided by log base e of a, where a is the base. And if you have a very unique calculator, and it has log base 17, 3, and 2. We have our calculator that, believe it or not, has log base pi. These divisions are all going to be equal, and you can calculate them if you have those two special a calculator that has log base 17 and log base pi. But for us mortals, it's gonna be those two. So if somebody asks you what log base 2 of 3 is, you could use your calculator to find it. You can't do this by hand. It isn't like you can suffer through multiplying two 5-digit numbers and get the answer. You can't do it. So you have log base c of a. Well, let's stay in alphabetical order. Log base a of b. This is equal to log base c of b divided by log base c of a. Now, this might be a little bit hard to prove, but if it's true, then that product is equal to the numerator, just like 2 is equal to 10 over 5, and 5 times 2 really does equal 10. So this is the same as log base c of a times log base a of b is equal to log base c of b. Now notice something. Those are the same. Let me write it down here. Those are the same. They kind of cancel out and you get CB. Log base C of B. Exactly what we said. So we're going to prove this one right here. Oops. We're going to prove this right here. How about I call that U and I call that V. And my goal is to get base C. So this tells me that A to the U is C. And this tells me that A to the V is B. So C is A to the U. Now, what do I do from here? Well, this here tells me that A is B to the 1 over B. So I write A any way any other way, and I have to raise it to the u power. Another way of writing a is b to the 1 over v. So this is equal to b to the u over v. That is, c is equal to b to the u over v. Or c to the v over u is b. This tells me that log base c of b is equal to v over u. That is, c to this power is equal to b. Exactly what it says. So, log base c of b is u over v. U was log base c of a. Log base c of a over v, which is log base a of b. Log base a of b. Now, we have this, but is that what we want? If you look at what well, let me see something. Okay, well, we said we're going to prove this. And one side should just have log base c of b. Oops, and it does. But somehow, it's not u times v. So what did I do wrong? Let us try this again. Now, my biggest problem is I have u over v, and I want to have u times v. Keeping the same base and multiplying, a to the u times a to the v is bc. C times b is bc. A to the u times a to the v is a to the u times a to the v. So the left side is this, and it equals bc. So log base a of bc is u plus v. Okay, so now we want to look to see if I wrote this wrong. Okay, I drew on it a lot, but what I have here is 100% valid. Let's write it again. And let's see where I'm making a silly mistake. This product should equal to the numerator. Oh, that's an A, excuse me. Okay, so this log base c of a times this log base a of b should equal to the numerator, log base c of b. Try again. I call this u, and I call that v. And I want uv to equal that. So let's try to keep our eye on that, the goal. I want uv to equal log base c of b. This is what we want. By the way, this is equivalent, this is equivalent of that. Okay, so now we have that. That's u and that's v. So c to the u is equal to a, and a to the v is equal to b. Okay, so we have c to the u is a. If I raise this to the v power, I get b. That is c to the uv is b. But that's where everything comes together. We have that log base c of b is uv. C to the uv is equal to b. Exactly what that line says. So log base c of b is u, which is log base c of a times v, which is log base a of b. And that's exactly what I wanted to establish. Log base c of b, which is right here, is equal to this times that. Okay, this is called the change your base formula. You can change the base. And again, if this statement here is true, then this statement is true. So I change from base A to base C. And now you can calculate things fairly easily with your calculator. Don't usually advise students to use a calculator, but I guess in these problems you have to. Somebody asks you what is log base 2 of 7. Well, you have no idea what to raise the 2 to get 7. 2 to what power is 7? I don't know. Now, if these had common, if I can write those with common bases, that would be drastically different. I would suggest that you don't use a calculator. Now, you can use a calculator for that. Now, what was the statement I just made? If you have log base 9 of 27, what do you raise 9 to get 27? I mean, you really should be able to handle it. If you take the second root of 9, you get 3. So far that equals 3. And if you cube it, you'll get 27. So this is 3 over 2. But you may argue that that's hard. Okay, fine. Think of the base as 3 squared, and think of the 27 as 3 cubed. And this is x. So you have 3 squared raised to the x is 3 cubed. The left side is 3 to the 2x, and that equals 3 cubed. You can't raise the same base to different powers and get equality. Since the bases are the same, the powers have to be equal. 2x is 3, the x is 3 over 2. Okay. If a to the b equals a to the c, then b equals c. B equals c, provided that a is not 0 and a is not 1. See, remember, 1 to the 7, which is 1, is equal 1 to the 11. But this does not imply that 7 equals 11. 0 to the 7 is 0. 0 to the 11 is 0. These are equal. I'm not going to argue that. But it does not imply that 7 equals 11. Okay? As long as a is not 0 or 1. If a to a power equals a to a power and a is neither 0 nor 1, then the powers are equal. And the good thing is, when it comes to logs, the bases have to be positive. let's look at that again. What if the base is 1? Okay. 1 to the 2, what is this equal? 1 squared is x, but x is 1. If I had 12 here, 1 to the 12 equals x, but 1 to the 12 is 1. If I had 121, 1 to the 121 is 1, which equals x. The x is always 1. So earlier, I said that a has to be positive. You might want to include that a is not 1. But even if a is 1, it works out. This number is always going to be 1. Because 1 to any power, including the square root of 2, 1 to any power is 1. So the only time the base can be 1 is if this number here is 1. And here you can have any number. So it's kind of boring. So I assume that they say a cannot be 1. But that's not a big deal, because you won't see a equals 1. And even if you did, it works out. It works out. Log base 1. The only thing is, if you have something like this, you can't solve it. 1 to the x equals 3. 1 equals 3. No. So it's a very boring base. So some people might define logs where the base can't be 1. Okay. So again, b has to be positive, c is any real number, and a, it has to be greater than 0, but it can't be 1. It can't be 1. It makes no sense for the base to be 1. So now that we proved a lot of these theorems, which is very important, how about if somebody were to ask you, here's a calculator real quickly, if need be, calculate that. And you can do ln of 7 over ln of 3 and get a very good approximation. Or you can do log base 7 over log base 3. That's called the change of base formula. Now, if you had log base 3 of 8, well, I don't know what to raise 3 to get 8, nor can I get those that have a common base. So I'll immediately say, well, need a calculator. This is log 8 over log 3, and I meant to say that will give you an approximation. Up here, equal, 100% equal. But once you use that calculator, it gives you an approximate answer. Here, we want to talk about expanding. Expand this. Well, you have log of a times b. This is log a plus, because it's being multiplied, log b. And the base does not change. It is 7. You have log base a of 8 is the 17. There's a couple of ways you can do this. A to what power equals a to the 17. Well, a to the 17 is equal to a to the 17, so the answer is 17. Now, I guess if a were 1, well, this would be 1, and 1 to the 17 is 1. This, well, no, this would have to be, see, this is the problem here, is now we get two answers, 0 or 1, because 1 to the 0 is 1, so that's allowed, and 1 to the 1 is also 1, so yeah, we can't let the base be 1. It isn't because it's boring, it's because it doesn't work. It's no longer a function. You get back two different answers. Okay. Now, another way to have done this problem is to realize the power can come down in front, and this is 1, because what do you raise a to get a? Well, a is a to the 1. Oh, you raise it to 1. So 17 times 1, which is 17. But we already established that that's always 1. Okay. So let's expand this one. Suppose you have log base c of x plus 1 over x minus 1. So the top is a, the bottom is b. We have log a over b. This is equal to log a minus log b. Same base, in this case c. Remember, we can only do that if this is positive and that is positive. That means x is bigger than 1. Suppose you have log AB over CD. We'll do this the long way. It's log of the numerator minus log of the denominator. But log of a product is log of the first plus log of the second minus log of a product is log of C plus log of D. And this becomes log A plus log B minus log C minus a positive log D, that is minus log D. Now, the question is, how can we go from the start right to the finish without doing all that work? Well, the four things are being multiplied. If it's in the numerator, there's a plus. There was positive log A plus log B. In the bottom, you get a minus in front. And it minus log C minus log D. Exactly what we have there. So, somebody were to ask you, what is log of EF over GH? This should be routine. The E's on the top, so it's positive log E. Don't have to write the plus. But now you do. Plus log F minus, it's in the bottom, minus log G minus log H. And if you have log AB over CDE, it's log A, because it's in the top, I didn't say minus, plus log B, because it's in the top, minus log C, minus because it's in the bottom, minus log D, minus log E, because they're in the bottom. Now, if you had something like log of A times B plus C over D times E plus F, these are the quantities in top that are being multiplied, and these are the quantities in the bottom that are being multiplied. Don't let the name of these factors bother you. It's going to be log A plus log B plus C minus log D, because it's in the bottom, minus log E plus F, because that's what I called this factor, E plus F. Don't let the names bother you. Just know where the multiplication is. It's this times that over this times that. So I wrote log of this plus the log of that minus the log of this minus the log of that. So now, what happens if I put exponents? A to the R, B to the S, C to the T, and D to the U. Again, we'll take this slowly. From what we just learned, this is log of the first factor plus log of the second factor minus, because it's in the bottom, the log of the third factor minus the log of D to the U. But we know that we can bring the powers in front. Okay, see that coming. So it's R log A plus S log B minus T log C minus U log D. So, kind of look at what's going on here. It's log of this, but the R can come out in front, plus the log of that, but the S can come out in front, minus the log of this, but the T can come in front of the log, minus log of D to the U. The U I can put in front. And there it is. You really should be able to go from here to there. It's not that bad. It's log of this plus log of that minus log of this minus log of that. And the this and the that, they all have powers, which can be brought in front. So when you go to write down this, anticipate the R coming in front. When you go to write this, bring the S in front, bring the T in front, bring the U in front, or if you prefer, take 9 steps. I mean, that's not a big deal with me at all. Okay, I mean, we could say it's the log of the numerator minus log of the denominator. Nothing wrong with that. And we have a product, so it's log of A to the R plus log of B to the S minus, we have our product. Now we have to take away all of this, and all of this is, since the product is the log of C to the T plus the log of D to the U. This is equal to log A to the R plus log B to the S minus log base C to the T minus log base D to the U. Now we can bring all the exponents in front of the logs. This is fine. It's a sign of a strong student. Okay? We used every rule to break it down. You don't always have to do it quickly, but if you can, go for it. Now, in this problem, we're gonna put it together. We're gonna not expand it, but write it with 1 log. Now, I have no idea what log 2 is, because I don't know what to raise 10 to get 2. I mean, I know 10 to the 0 is 1, and 10 to the 1 is 10. To get 2, the power is going to have to be between 0 and 1. I have no idea what that is. And when it comes to log base 10 of 5, I don't know what to raise 10 to get 5. And it is not a half. 10 to the half is the square root of 5. Now once again, 10 to the 0 is 1, 10 to the 1 is 10, 5's in the middle. So the power is going to be in the middle. But you know what? Since it's addition and the bases are the same, I can take log of 2 times 5, which is log of 10. And you should know that 10 to the first power gives you back 10. So sometimes combining them is a lot quicker than running and getting a calculator. Okay, I mean, 2 times 5 isn't bad. So you get to this right away. Oh, that's 1. If you have log base 2 of 117 minus log base 2 of 7, and you're not allowed to use a calculator, well, then I would think, well, this is log base 2 of 117 over 7. And then I'll say, well, this must be a nice number. 7 into 117, 1 time 7 into that. Maybe it'll be better if that was 119. 7 into 119 goes 17 times, but I'd love for it to go 16 times. 70 and 42. Okay, I apologize. Let's make this number 112. Let's make that number 112. When we do 7 into 112, goes 1 time, 4 left over, 6 times. So this is just 16. Well, 2 to what power gives you 16? Well, it's 4. 2 times 2 is 4, times another 4. 4 times 4, 16. So the answer is 4. Okay, so you can do that without a calculator if that's the instructions. If you have log base 12 of 9 plus log base 12 is 16, and you can't use a calculator, well then you better hope that that number in the brackets is 12 to some power. And turns out that 16 times 9 is 144. And you should know that 12 times 12 is 144. But 12 times 12 is 12 squared. So 12 raised to the second power is equal to 144. Now, let us prove another fact. I claim that a raised to the log base a of anything is equal to the anything. Just remember that what you take the log of has to be positive. So, I want to prove that a raised to the log a of x is equal to x. And I'm hoping the proof isn't very complicated. So I have a log a of x is equal to x. So I take log base a of both sides. Log base a of x. Now, what happened is, this and this is just going to be log base a of x. Or you can bring the power down in front, so then you get log base a of x times log base a of a is equal to log base a of x. I got what's going on. This statement is true if and only if that statement is true. But this last statement is true because that's 1. And log base a of x times 1 is log base a of x. And it certainly equals that. So it turns out that they're all true. Okay, as long as if you say this is equal to that, and then you do legal things, you multiply both sides by 2, you take the square root of both sides, and you take log of both sides, and then you get 7 is equal to 7, which is true. That means the beginning is true. Just for the record, if you get 7 equals 17, then it's not true. And, if you get x plus 7 is equal to x plus 7, it's true. That last statement is true. That means all the earliest statements were true. Of course, if you multiply the left side by 7 and the right side by 3, there's no reason to assume after you make a mistake like that, and then you conclude that x equals x. That's nonsense, because 3 times this equals 7 times that does not follow. It doesn't follow. See, this may imply the second line. It may imply the third line. It may imply x equal x. But the beginning line doesn't imply the second line. You can't, if in fact these are equal, and you multiply by 3 and 7, they shouldn't now magically become equal. Okay. So how would you simplify this? Remember that log base a raised to the log base a of x is just x. So how would you simplify 10 raised to the 2 log 3? Keep in mind that there's an understood 10 here. So these are the same, just like those are. The thing is this here is not in this form. There's no number that's over here. So what you need to do is realize that that's 3 squared. That is, this is 10 log base 10 of 9. Now it's in the form a log base a of a number is equal to the number. A log raised to the log a of a number is the number. You can't deal with that 2 out there. that 2's really messing things up. Now, I guess what you can do is, that won't work. Yeah, what if you think of it as log base 10 of 3 squared? You can do it that way as well, because you're supposed to multiply the powers, and here you do get 2 log 3 when you multiply them. Here, the inside is in the form of our formula. Base times log of the same base equals a number. That number is 3. But whatever is in here, you have to square it. And you do get 9. Same answer. I just think it's easier to, either way you had to square this 3, I would square it right away. If you were asked to calculate log base 5 of 25 minus log base pi, or 5, in as few steps. I mean, you can always go, well, that's log of 25 over log 10 minus log pi, minus log of 5 over log pi. But that would calculate, you had to do a division, 2 divisions, 2 divisions, and 1 subtraction. If you divide the 2, you'll get log base 5 of 5. So I did 1 division. That's it. I just did 1 division. Here I did 2 divisions with my calculator, and then I did a subtraction. Here I just did 1 division, and I got 5. So, would you rather do 1 division or 2 division and 1 subtraction? Okay, and it's a pain to do division with subtraction. You got 7 over 2 minus 5 over 3. You might do 7 divided by 2 minus 5 divided by 3. And depending upon how you do it, your calculator might do this and then divide that by 3. That's not what you want. Okay? I wouldn't subtract the division. It's much easier to say 25 over 5 is 5. Boom. Oh, so I guess you do have one more division. I apologize. This is equal to log 5 over log pi. So you have 2 divisions. You did save a subtraction. Why do you have 2 divisions? Because you can't calculate this in your calculator. But you can certainly calculate that. And if for some unfortunate reason your log button broke, you can always go log 10, log base e. Let's talk about that for a moment. If somebody asks you to calculate log of 7 and your calculator, the log button isn't working, so just remember that's base 10, but your ln button is working. There it is. Crank it through. Likewise, if you're asked to calculate ln of 3, which is shorthand for log base e of 3, if your ln button isn't working, it's log 3 over log e, and this the 10. And remember, this is not 1, because 10 to the 1 is 10, which doesn't equal e. Okay, I have no idea what to raise 10 to, to get approximately 2.718. Once again, 10 to the 0 is 1, 10 to the 1 is 10. This number is somewhere in the middle. So I guarantee you the power, whatever this number is, it'll be bigger than 0 and less than 1. I have no idea. Besides, that's not even the complete number. It repeats, not repeats, it goes on forever and ever. Okay, this finishes the section on law of logs.